Bismillahirrahmanirrahim. Assalamu alaikum and welcome to this session. In this session, we are going to talk about hypothesis testing, which is at the very heart of the scientific method. In the scientific method, we propose hypotheses to explain away aspects of observed nature. And we have these hypotheses as tentative explanations of how things are working and why we are producing the results that we are. So the important thing here is that these hypotheses are tentative. And so because of that, we may have a better hypothesis, and then we have to test the new hypothesis, and we should only accept the new hypothesis after rigorously testing it. So the key idea here is that we should not be rejecting the old hypothesis for the new hypothesis just on the basis of some chance occurrence. So it may be that the chance occurrence is producing empirical results that are consistent with the alternative hypothesis, but the real alternative hypothesis effect is not present. So we must rule out chance as a factor so that we do not attribute causal effects to just purely coincidence. So the general idea then of hypothesis testing is that we do not accept any hypothesis until it is very rigorously tested. Because all of the scientific method is based on hypothesis and on proposing hypothesis, this is a very important part of the scientific method. How do we determine if a hypothesis is indeed tenable and if we should adopt it or if we should be rejecting it? So to explain away the intuition of hypothesis, in the first part of today's session, we are going to talk about the intuition of hypothesis testing. I'm going to build this intuition by talking of an analogy of the legal system. And we'll be seeing how we have parallels between the legal system and the statistical method of hypothesis testing, which we use in network performance evaluation. In the second part of today's session, we're going to talk about kinds of tests and test statistics that we use to formally analyze a hypothesis and decide if we should be rejecting the null hypothesis or if we would be failing to reject the null hypothesis. So we start with the first part, in which we're going to build intuition about hypothesis testing. So the analogy we are going to use is the Pakistani legal system, which is based on the Commonwealth legal system adopted in other countries as well, such as US and UK. The general idea here is that you have an adversarial system in which whenever someone is accused of a crime, you have two parties that present their case before an impartial judge. So these two parties are named as defense and as prosecutors. Defense is trying to defend the accused person, and the prosecutors are trying to prosecute or to prove that the accused person is guilty. And the assumption here is that the person is assumed innocent until it is proven beyond reasonable doubt that the person is in fact guilty. And in that case, we can prosecute the person. In a similar vein, if we think of hypothesis testing in network performance evaluation, we have what is known as a null hypothesis. This is the default hypothesis, whatever we believe in currently. And then we have an alternative hypothesis. This is something that we want to prove. Until and unless we have very strong evidence which conclusively tells us that the alternative hypothesis must be adopted, we would stick with the null hypothesis. But it must be made very clear that in network performance evaluation, our evidence is going to be probabilistic in nature. It would be very rare for us to know for certain if this algorithm performs better than the existing algorithm. This is because in most cases we are only working with samples. And when we are talking about samples and then inferring about populations, there is always an element of chance that due to just chance, we may have a sample which is not representative completely of the population. And therefore, we must take this error into account. So on the slide now you can see the analogy that we're trying to build. You see that we are trying to judge if a person is innocent or if he is guilty. So if we catch someone, we want to ascertain if that person is innocent or if that person is guilty. The default assumption or the null hypothesis is of innocence. And this null hypothesis stands until we can establish alternative hypothesis, and when we have evidence towards that effect, we can then reject the null hypothesis. We must stress here that rejecting the null hypothesis does not mean that we have proved the null hypothesis to be wrong. Similarly, when we reject the null hypothesis and we adopt the alternative hypothesis, we have not proved that the alternative hypothesis is in fact true. This hypothesis testing is not in the realm of mathematics in which we are trying to prove things, but this is in the realm of statistics where we're trying to make probabilistic decisions, and therefore it is possible that we make error in doing this judgment of hypothesis testing, and that shall come later on in today's session. Let's now try to determine what are the possible judgment scenarios and what possible errors can we make. So if you see on the slide now, you would see that our null hypothesis, the thing that we believe in if we cannot prove otherwise, is that the accused person is innocent. The alternative hypothesis represented here by HA, whereas null hypothesis was represented by H0, the alternative hypothesis is that the person is indeed guilty. So let's see how the judgment can go. The truth can be that the accused person is in fact innocent and he may be assumed guilty when we actually judge. So this is the scenario shown on the left top side. We can also have the person guilty and he is also now assumed guilty. So this is the second possible scenario. We can have the person actually innocent and he is assumed innocent. And lastly, the person may be actually guilty, but he may be let go scot-free by the judgment when we say that that person is innocent. So there are 4 possible judgment scenarios, and 2 of them are correct decisions. So the first correct decision is the top right scenario, in which the person is guilty and we also assume that that person is guilty. The other correct decision is the bottom left scenario, in which the person is innocent and we let go of that person and we assume that that person is innocent. So these are the correct decisions, but we can also err, and we can err in 2 directions. So the first error we can make is that we assume that the innocent person, the actually innocent person, is guilty, and this is known as the type 1 error. So this is unimaginatively named, so type 1 error will not indicate as such what this error is about. So you can think of this as a false positive. In the terminology of statistical hypothesis testing, a positive result happens when we reject the null hypothesis and we accept the alternative hypothesis. The other kind of result is known as a negative result or a null result, in which we fail to reject the null hypothesis and thereby we fail to accept or adopt the alternative hypothesis. So the type 1 error is known as a false positive because it is giving a positive result in that we are adopting the alternative hypothesis, but this is a false result because the null hypothesis was in fact true. And while the null hypothesis was true, we made an error and we rejected that, and therefore this is an error. The kind of error this is named as the type 1 error. The other kind of error is that we can err in the opposite direction. It may be that the person is actually guilty, but we judge that person to be innocent. So this, in the context of the null hypothesis and the alternative hypothesis, would be that in fact the alternative hypothesis should have been adopted. We should have rejected the null hypothesis, but we fail to reject the null hypothesis. So this is also an error, but this is in the other extreme to the type 1 error. So this is known as the type 2 error. And we would see that, in fact, these two errors are in conflict with each other in some sense. We would see that if we try to reduce the type 1 error, we tend to increase the type 2 error. So if we want to reduce the chances of prosecuting an innocent person, it is also probable that we will let go some people who are actually guilty. And it also works the other way around. So let us now see how is the null hypothesis evaluated. In this case, because the null hypothesis is the innocence of the person, we are interested in seeing how can we judge or ascertain the innocence of the accused person. So you can see on the slide now, you would see that we have on the x-axis impact of testimony. So the idea here is that you have caught a person and that person is in fact innocent. So we are assuming that we know the truth, that that person is innocent, but because that person is caught, it is probable that that person is a victim of circumstantial evidences. So the probability of obtaining testimony is shown on the y-axis. The extreme impacts are those that we are interested in. On the right side of the graph, we have highly credible testimony that is proving the person to be guilty. And on the other side, the left-hand side, we have highly credible testimony that is proving the person to be innocent. So if you recall, I said that we know the actual person is innocent. So how do we go about evaluating the innocence of this person? So as we know, we say that law is blind. So the actual judgment is based on the evidence that is presented. If highly credible testimony is presented that proves in a sense that that person is guilty, then we would actually be prosecuting that person. So this is a kind of an error. But we can see that the probability of having this error is very less. So you would see the portion of the graph which is on the right hand side, the reddish hue part, we would see that the probability of this is less. The area under that part of the curve is less. So we accept that there may be some errors. It may be that the real person is innocent, but because of chance occurrences only, it may be that the circumstantial evidence tends to show that that person is accused. But this will happen very rarely. And we accept this because we cannot be 100% sure, because it is going to be very rare that we find certain evidence that shows with certainty that a person is innocent or guilty. If we were to expect 100% certainty, we would be able to prosecute very few criminals, because whenever criminals are caught, they only have limited evidence against them, unless the crime was committed before many people and there were many people who saw the crime with their eyes. In the usual case, we would only have limited people. We would have evidence, but that evidence is not certain. So the idea is we want to establish beyond reasonable doubt, and only then we can prosecute a person. So a reasonable doubt is defined as in a reasonable person would not have a reasonable doubt that that person is in fact innocent. The evidence is so conclusive, or it is giving us virtual certainty, and therefore on the basis of that we can judge that person to be guilty. But it must be remembered that we can make an error, and that error, as I pointed out, is the reddish part of the graph here. So if you see on the slide now, we have now demarcated and have shown a threshold which is known as the standard of judgment. As mentioned before, we want to prosecute criminals. If we were expecting 100% evidence before we could prosecute someone, we could prosecute very few criminals. So we then set a standard. We would say that, okay, if we are 95% sure that this person is actually guilty, then we can go ahead and prosecute that person. The chances of error would still remain. If we are insisting on 95% confidence, we would still have 5% chance of making an error. And when we make that error, this is known as a type 1 error. We are prosecuting an innocent person. So you can see on the slide the type 1 error, which is highlighted as the reddish part under the right hand side of the curve. And we see that we have set an arbitrary threshold. So this is important. If we want to be more certain of the fact that the person is actually guilty before we prosecute that person, it is probable that we would also let go of guilty people. So we have to then define this threshold, because as you would see very soon, that this standard not only affects the type 1 error, but it also affects the type 2 error, in which we fail to reject the null hypothesis. In this analogy, a type 2 error would mean we would fail to prosecute a guilty person. So on the left hand side of this demarcation, you have the not guilty verdict. And you would only have a guilty verdict when either you have a very credible evidence which is telling us that the null hypothesis of innocence must be rejected, or you have very extenuating circumstances in which the null hypothesis might be true, but the evidence is strongly against it. So I hope the type 1 error is clarified from this slide. So the point here is then that the standard of judgment is an arbitrary threshold criterion, beyond which we will term the evidence as very unlikely if the null hypothesis was true. And on the screen, you can also see the type 1 error rate. This is also known as the significance level, or alpha. And this is the probability of rejecting the null hypothesis when it is in fact true. So this is the probability of making a type 1 error. This can also be referred to as the false rejection of the null hypothesis. We can also err on the other side, and this actually tells us the subtlety in the decision of making the threshold. How do we define the threshold? Because if we define the threshold to be very high, that let's say we will only prosecute when we are 99% certain, it is very probable that you would be letting go many guilty person, because as mentioned before, even for a guilty person, the chances of having conclusive evidence is going to be very rare. And therefore, while you're saving on making errors of type 1, you would be making more type 2 errors. So the idea then is that in many cases, the results of the null hypothesis and alternative hypothesis would be similar. In other words, if a person is guilty or if he is not guilty, the circumstantial evidence that is shown to you will not be conclusive. They may actually give you the same circumstantial evidence. And therefore, we need to be aware of these errors. And from this analogy, I hope and some intuition is built about type 1 and type 2 errors. And we would see that we have precisely these kinds of errors in statistical hypothesis testing, which we use in the field of statistics to determine if we should be continuing with the null hypothesis or if we should be adopting the alternative hypothesis. This also goes on to show what I talked about at the start of this session, that we should not be rejecting the null hypothesis on the basis of chance alone. We want to rule out chance as a player, and we would only be rejecting the null hypothesis and accepting the alternative hypothesis if we have strong evidence. Another important point here is the effect of the sample size. So as in the legal system, when you have multiple witnesses corroborating each other's version, or they are confirming whatever is being said by other witnesses, the weight in the evidence increases. Similarly, when we are doing hypothesis testing, we are doing this test on the basis of a test statistic that is calculated on a sample. So the size of the sample is very important. If we increase the size of the sample, the weight of the evidence also increases. So as you can see on the slide, it is easier to establish the alternative hypothesis when the sample size is larger. And you can see that we can now more clearly distinguish between innocence and being guilty when we have multiple evidences. The multiple evidence adds to each other and the impact of the testimony increases. So now we come to how significance testing is actually done in network performance evaluation. So in network performance evaluation studies, typically we are interested in seeing the efficacy of certain algorithm that you are designing. We want to see how good a system is that you are designing, and we want to compare it to the status quo. So let's say the status quo here would be the system without the modification that you're proposing. So what we're really interested in is in showing that the alternative hypothesis should be adopted. So when we're doing network performance evaluation, we're interested in positive results, when we can reject the null hypothesis and accept or adopt the alternative hypothesis that there is indeed some effect. So on the slide now you can see the null hypothesis. It states that the new algorithm produces no change. The alternative hypothesis is that the new algorithm does produce change. So what we're interested in is a positive result, and that actually shows that we have an effective algorithm, and that is exciting. The other aspect would be when we have a null result or a negative result. That is considered boring, and we do not want that result typically if we are doing a hypothesis test to check the efficacy of our own algorithm. So in that sense, it is in fact important to have a positive result. That is what we are interested in. So in this new context, let's now see what are the kinds of errors we can have. So the null hypothesis is that the new algorithm does not have any effect, or we may say that it is ineffective. The alternative hypothesis is that the new algorithm is effective. So the truth may be that in fact the null hypothesis is true, or it also may be that the null hypothesis is not true. So we have to make a decision. We have to either reject the null hypothesis, or we will fail to reject the null hypothesis. So all these scenarios are shown on the slide. You see that on the left top side, you have the case where even an ineffective algorithm is assumed as effective. So this produces a false positive result. On the top right side, you have assumption of effectiveness when you actually have an effective algorithm. So this is a correct decision. If you see the bottom left scenario, we have an ineffective algorithm and it is judged to be ineffective. So you would fail to reject the null hypothesis, and that is the correct decision. But the other error that we can make is that we can, even when the algorithm was effective, we judge it to be ineffective, and that is a very bad experience if you are a researcher where your effective algorithm is judged to be ineffective. So let's now give them the names that we have seen. We see that the top right and the bottom left scenarios are the correct decisions, and the other two decisions have errors. The top left one is the type 1 error, in which we are rejecting the null hypothesis when we should have adopted the null hypothesis. And the other error is the type 2 error, in which we fail to reject the null hypothesis when we should have rejected the null hypothesis. In the context of our new setting, we are assuming inefficacy when actually the algorithm is effective. We also see that type 1 errors will occur with probability alpha, which is defined as the significance level. And type 2 error will occur with probability beta. And we would see that these two probabilities are in somewhat of a conflict with each other. So with this, we come to the end of the first part, and now we'd be talking about the various types of tests that we have and the various kinds of test statistics. So first of all, let me tell you about the steps of doing hypothesis testing. So you can see this on the slide now. The first thing that you need to do is to set up the null and alternative hypothesis. And often alternative hypothesis is the effect that you want to actually prove. And the null hypothesis is that there is no such effect. And you want to test the null hypothesis. So this is very important. हमारी सारी जो hypothesis testing है वो actually null hypothesis पे हो रही है. We would either reject the null hypothesis or we will fail to reject the null hypothesis. If we reject the null hypothesis, this actually gives credibility to the alternative hypothesis. और जो null hypothesis की testing है उसमें जो हम टेस्ट किस किस्म का करेंगे उसमें अल्टरनेटिव हाइपोथेसिस का पार्ट तो कुछ है पर हम हाइपोथेसिस टेस्टिंग में टेस्ट सिर्फ नल हाइपोथेसिस ही को कर रहे हैं. उसके अलावा द सेकंड स्टेप इज द setting of the level of significance. So we have to define alpha or the probability of falsely rejecting the null hypothesis. So these are the first two important steps, and then the next two steps are what I'm going to focus on in this session. And the third step is defining of the test statistic and the rejection region. तो एक और चीज़ इम्पॉर्टेंट ये है कि एक चीज़ मैंने बताई कि हाइपोथेसिस टेस्टिंग हम नल हाइपोथेसिस पे करते हैं. सेकेंडली एन इम्पॉर्टेंट कॉन्सेप्ट दैट यू मस्ट अंडरस्टैंड इज व्हेन वी आर डूइंग हाइपोथेसिस टेस्टिंग वी आर एक्चुअली डूइंग इन्फरेंशियल स्टैटिस्टिक्स. Based on a sample, we're trying to make some inference about a population parameter. So always when we define a null hypothesis, it is in terms of a population parameter. And the data that we have is actually just a sample. And we want to make conclusions about the population based on just the sample. इसके लिए हमें एक statistic calculate करना पड़ेगा. And that depends on the kind of test you're doing. So there are multiple kinds of hypothesis test. एक hypothesis test ये हो सकता है कि we say that the population mean is this, some given value, and we are going to focus on just this test for today, but there are other tests. For example, we can say that the real population parameter for so and so is this much, and we want to check if that is actually the case. And we may also be interested in only one-sided test in which we are alternative hypothesis is that the real value as indicated by the null hypothesis is not that value, but it is higher than that. This may be an alternative hypothesis. Your alternative hypothesis may also be that the real value, the real population parameter is not equal to the parameter that is hypothesized by the null hypothesis. तो इसके बारे में हम देखेंगे कि both tail tests भी होते हैं, आपके पास single tail tests भी होते हैं, उनकी क्या significance है. But the general idea is कि आप sample के ऊपर एक test statistic calculate करते हैं. उसके बाद आप उसको compare करते हैं with what you expect if the null hypothesis was true. And if the test statistic is very extreme, then you can actually reject the null hypothesis. And this is the fundamental concept of hypothesis testing. So let me repeat this then, that you calculate the test statistic and you compare it with what you would expect if the null hypothesis was true. And if your test statistic is very extreme, this gives us credibility in rejecting the null hypothesis and adopting the alternative hypothesis. Also, when we've completed this, then we have gathered evidence and we can then state a conclusion for the original question that we want to answer in the hypothesis test that we're performing. So, test statistic ke baare mein, I've already mentioned that it is computed on samples. So, and it is from the sample we determine a statistic and then we compare it what we would expect to have. If it is very extreme, we would say that, okay, maybe the null hypothesis is not a good explanation of this, so we will reject the null hypothesis. अब question रहता है कि कौन-कौन से test statistic exist करते हैं. So there are many different test statistics and I'm just going to focus on one, and that is the Z statistic. So you may remember from a previous session in which we talk of the Z value. Normal distribution की एक interesting बात ये है कि we can, for all the different kinds of normal distributions, because normal distribution is a family of distributions, for each distinct value of mean and variance, you would have a different distribution, but you can always standardize them. And you can talk in terms of what is the distance of a value in terms of standard deviation from the mean. So if you do that, you have what is known as the Z distribution, and we can calculate Z statistics on the basis of this. So isko hum abhi develop karenge, and we'd be actually using this concept or this statistic in today's session, but there are also other statistics. If we recall, when we talked of sampling, we said that the sampling distribution is a normal distribution only when we have large samples. So because we're going to use this Z statistic today, we're also assuming that we have large sample, and we also are assuming that either the value of sigma is known. This would be in the case when you have a small sample. If you have a small sample and if you have the parent distribution is normal, you can assume that the sampling distribution is normal. So this is an assumption that we make. हम assume कर रहे हैं कि sampling distribution normal है, और sampling distribution को normal रखने के लिए जो assumptions हम बात कर चुके हैं in the sampling session, all of those assumptions we're also making. So with this caveat, let's begin our discussion on the Z statistic. So to understand the Z statistic, have a look at the sampling distribution of the sample mean. So as discussed during the session on sampling, the sampling distribution gets the shape of a normal curve as you increase the size of the sample. So this is a normal curve, and for any normal curve with a given value of mean and given value of standard deviation, we can always employ the empirical rule to calculate the number of values which would fall in a certain range. So you can see in this slide that 95% of all sample means would actually be within 1.96 standard errors of the population mean. So इस case में 95% इस range में आ रहे हैं. And if you happen to get a value which is further away from this, अगर sampling distribution ये है, so let us spend some time to develop intuition of what a sampling distribution of the sample mean means. इसका मतलब ये है कि we know that the sample mean is a random variable. If you take different samples, you would have a different sample mean. So what is the probability distribution of this sample mean? तो उसको हम define करते हैं by the sampling distribution. And using this information, we can then see how rare would a particular value of a sample mean would be, because as can be seen in the slide, 95% of all sample means would be inside 1.96 standard errors of the mean. So if we calculate this range, most of the sample means would be in this interval. And if you have a sample mean outside this interval, so that would mean you have a rare occurrence. And based on the standard of judgment that you have, you can then either decide to take that as an evidence that particular mean is not from this distribution. So इसको हम समझने के लिए we need to understand what is the concept of acceptance region and rejection region. So before we get to that, we need to first of all again reiterate कि hypothesis testing जो है वो null hypothesis को test करती है. So imagine it's a statement about the population sample mean and you're hypothesizing that it is a value of 0. Now you want to check this hypothesis. आप किस तरह check कर सकते हैं कि वाकई population mean असल में 0 है. So to do that, you would take a sample. And if your sample is close to what you would expect, assuming that the population mean is 0, that would give us evidence that maybe the null hypothesis is right. But if you get a sample mean which is so extreme, given the null hypothesis, it may actually give you some evidence for rejecting the null hypothesis. And this is the basis of hypothesis testing. So imagine that you get a sample mean having a z-score value of 1.8. Z-score value क्या है? It's how many standard errors you are away from the mean. And we've already seen that 95% of all sample means would be inside plus minus 1.96 standard errors of the mean. So with this thing in mind, we want to see how rare is this sample and can we reject the null hypothesis on the basis of this? To do that, we need to first of all define our significance level. कि कितनी probability हम बर्दाश्त कर सकते हैं of falsely rejecting the null hypothesis. So when we do that, and usually this is taken to be 5%, a significance level of 0.05 is taken, where you say that we're okay with rejecting 5% of, we're okay with rejecting falsely 5% of the null hypothesis when it is actually true, so that we can actually reject the null hypothesis and in certain cases adopt the alternative hypothesis. So now we are in a position to discuss acceptance and rejection region. And why are we discussing this? It's very important to stress on this. It's because we want to see our test statistic, how extreme is it. If it is very extreme, we can reject the null hypothesis. If it is not very extreme, we would say we will accept the null hypothesis or we will fail to reject the null hypothesis. तो ये दो region हम define करते हैं. उसके बाद whenever we have a sample mean, we would see in which area does it lie. If it lies in the rejection region, we can then say that the null hypothesis is rejected and we are going to adopt the alternative hypothesis because the result that we have is untenable if we consider that the null hypothesis is actually true. When I say untenable, what it means is not impossible. Obviously, you can still have, but the probability of having such an extreme result is negligibly small, and we define this amount of negligibly small by defining the significance level or the value of alpha. So rejection region can actually be either two-tailed or it can be one-tailed. इसका मतलब ये है because normal distribution is symmetrical. तो इसलिए आपकी जो sampling distribution है वो symmetrical होती है. So you have values on both sides of the center. So if we're interested only in showing that the alternative hypothesis is that the real population parameter is more than that hypothesized in the null hypothesis. Alternatively, if we are interested in showing that the real population parameter is actually less than that hypothesized by the null hypothesis, this would be what is known as a one-tailed test. But we'll be first studying the two-tailed test. इसमें हम interested होते हैं in showing that the alternative hypothesis is that the real population parameter is not that what is hypothesized in the null hypothesis. यानी आप दोनों sides पर rejection region define कर सकते हैं. So assuming that your significance level is 5%, because of symmetry, you would have a region of 2.5% probability on one side and a region of probability 2.5% on the other side. And you would reject the null hypothesis if you happen to get test statistic in those rejection regions. So let's see this through an example. This is the slide shown. We have a graph in which we have the z-score of the statistic, and we already know that 95% of the test statistic would actually fall inside 1.96 standard errors of the mean. So this 1.96 is actually the critical value. Plus minus 1.96 जो values हैं वो separate कर रहे हैं the rejection region from the acceptance region. In the middle you have the acceptance region, and that is symmetric around the center. And on both the extreme tails, on the left hand side and on the right hand side, you have an area of 2.5% probability which you're classifying as a rejection region. You're saying that if I get a test statistic in this range, I would say that this is too extreme a result, and because of that it gives me evidence for rejecting the null hypothesis. So if you have a value of sample mean आपके पास जो आया उसका z-score 1.8 है, तो 1.8 is actually inside the acceptance region. So you will not reject the null hypothesis here, but you are very close to being in the rejection region. So इस case में you can say that the confidence that we have that null hypothesis is a good explanation of this is not very high, but it may also be that the null hypothesis is true and we have a relatively rare event, but still this event is not rare enough for us to reject the null hypothesis. Another point you must note is that while we are assuming in a null hypothesis the value population parameter is 0, इस केस में अल्टरनेटिव हाइपोथेसिस ये है कि असल में पॉपुलेशन पैरामीटर 0 नहीं है, लेकिन you can generalize this example to any value of the population parameter because in the figure we are actually using z scores. जब हम context में बात करते हैं तो we are only talking in terms of the test statistic being rare in terms of how far away is it from the sample mean in terms of standard errors. तो ये जो measure है वो standard है and you can adopt it in a general setting. So we've talked of the two-tailed test. Let's talk of the one-tailed test. So if your null hypothesis is that the value of mu is 0 and your alternative hypothesis is that the value of mu is actually more than 0. आपकी असल में hypothesis है कि value of mu is more than 0, but you want to convince someone of this claim, you need to first of all reject the null hypothesis. And to do that, you define the acceptance region and the rejection region. The rejection region would here be in the extreme right tail because you're interested कि आपके पास एक extreme value हो और वो इतनी दूर हो from the value that is hypothesized in the null hypothesis कि आप null hypothesis को reject कर सकें. But you can only have this extreme event on one side of normal curve. In this case, you see that this rejection region is on the right hand side and you have an area of alpha which is 5% and this is on the right hand side. So the question now is, what is the critical value which is separating the acceptance region from the rejection region? And this critical value is z is equal to 1.645. If you get a value of the z statistic which is actually more than 1.645, you would say that you are right in rejecting the null hypothesis according to the defined standard of significance level of 0.05. If we have a result of z is equal to 1.8, because this is in the rejection region, you can say that okay, we can reject the null hypothesis because our result is too extreme to be explained by the null hypothesis. We can also talk of the left tail test. इस केस में आपका जो critical z value होगी वो होगी -1.645 and because we are considering our example जिसमें z value जो है वो 1.8 है, this is clearly on the right hand side of the rejection region. This is clearly in the acceptance region. So we would be concluding that the null hypothesis is right and we have strong evidence for that because we are comfortably in the acceptance region. Having talked about acceptance and rejection region, we should now stand back and see what kind of information are we getting from these tests. So essentially the kind of information we are getting is of a binary kind. Either we are rejecting the null hypothesis or we fail to reject the null hypothesis. But it is not telling us by how much are we rejecting the null hypothesis or we are failing to reject the null hypothesis. It may be that you have failed to reject the null hypothesis, but you missed by a very small margin, or it may be that you missed by a very large margin. To distinguish between these two distinct cases, we have the concept of the p-values. The p-value is defined as the probability of getting results as extreme as those observed or even more extreme given that the null hypothesis is true. This last conditional statement is very important. P-value is not the probability that the null hypothesis is true. It's just that we are assuming that the null hypothesis is true and then we are saying what is the probability of getting results as extreme as those observed or even more extreme. So let us study p-values for the example we've been developing, both for the example of both tail tests and also for the single tail tests. So we start with the both tail test example, in which the null hypothesis is that the population mean is equal to 0, and the alternative hypothesis is that the actual population mean is not equal to 0. And we want to calculate the p-value for the sample mean that we've obtained of z-value of 1.8. So to calculate this, we would observe the probability of having results more extreme than this. And because this is a both tail test, we'd be observing for having a z-score value of plus 1.8 or more, or minus 1.8 or less. And we'd be summing up all this probability, and that would be the p-value of this statistic. So in this case, this comes out to be 0.0718, which is a low value, but it is not low enough to be rejected by the significance level of 0.05, because this is more than 0.05. But if we had only conducted the rejection and acceptance of the null hypothesis, this null hypothesis would have stood. But in this case, because we have a p-value of 0.0718, we are more confident that we failed to reject the null hypothesis, but still the results are quite extreme. Let us now study how we can calculate the p-value for a left tail test. For a left tail test, the alternative hypothesis is that the real value of the population parameter is less than that hypothesized in the null hypothesis. So if we see the slide here, we see that for a sample mean having a z-score value of 1.8, the p-value would be calculated as the area on the left-hand side of this. So if we determine the area under the curve on the left-hand side of this, it comes out to be equal to 0.964, which is a very high value. So we must stress here then that a high p-value actually indicates that the data is more in accordance with the null hypothesis. And if we have a very small value of the p-value, it is indicating that the results are very extreme, and the null hypothesis may not be a very good explanation of it. Also, as emphasized before, I reiterate that the p-value is not the probability that the null hypothesis is true, because in terms of frequentist probability, we do not attach probabilities to fixed variables, and also we do not attach probabilities to one-time events. In this case, the population parameter mu is actually a fixed variable. It is the sample statistic which is varying. So it is important that we do not confuse this matter. What we are actually doing is, as can be seen in this slide, we are calculating the probability of the data given that the hypothesis is true. So this is the p-value. We are not calculating the probability of the null hypothesis given the data. So there is a difference, and it's an important difference. So please do not confuse both of these things. Let's wrap up the discussion on p-values by talking about the right tail test. And for that, again, I refer back to the slide. If we have a value of z-score equal to 1.8, the p-value would be the area under the curve on the right-hand side of this, which would mean what is the probability of getting a result as extreme or even more extreme than this. And we're only considering the right tail. So this comes out to be 0.036, which is a very strong result, and this will result in the rejection of the null hypothesis. Any result which leads to the rejection of the null hypothesis is said to be statistically significant, which simply means that this result, the probability of obtaining this result only due to chance is very less. This does not talk about the practical significance of the result, only that this result is very rare considering only chance events. So, having talked about p-values, I will wrap up today's session by talking about the kinds of errors that we have and trying to build intuition about that by showing a simulation. There are basically two kinds of errors that we can make in statistical hypothesis testing: the type 1 error and the type 2 error. And I'm going to show you these in an example including a smoke detector, a toaster, and a fire. So let's see this example. In a usual household, we usually have smoke detectors the real purpose of which is to detect smoke coming out of fire. But often this smoke detector is activated from the smoke emanating from cooking. So we can understand the type 1 error and type 2 error in the context of this example. So the null hypothesis in this case is the status quo, that there is no fire. And the alternative hypothesis is that there is fire, and because of that, you reject the null hypothesis, or you create or you ring the alarm. So this would be a positive result when you ring the alarm. But this ringing of the alarm may be a false positive, because it may be that there is no fire. It is actually just someone cooking and the smoke coming out of it. So how do we actually adjust between these type 1 and type 2 errors? If our smoke detector is very sensitive, it is going to produce lots of false positives. But while it is doing that, it is also going to detect all fires. अगर हम ऐसा करें कि smoke detector को less sensitive बना दें, by maybe taking out the battery from it, what will happen is that we will not be getting any false positives. But because this is an extreme occurrence, we'd also not be having any true negatives. When you really have a fire, the smoke alarm will not be able to detect it. So in this case, when you have an alarm and there is no fire, this is an example of a type 1 error. And when you do not have any alarm, when there is an actual fire, this is known as a type 2 error. And I'm going to show you some simulation output to show you the trade-off between these two types of errors. So the first thing I want to talk about is that the type 1 error is actually influenced by our choice of alpha, or the significance level. So this figure that you can see on the slide needs some explaining. The normal curve that you see on the left hand side is built assuming that the null hypothesis is true, and the null hypothesis is saying that the mean value is 0. But we also have an alternative hypothesis, and the alternative hypothesis is that the difference between means is 3.3 something. So because of that, you see a difference between these two curves. You also see some intersecting areas between these two curves, and you have a single yellow region and you also have a red region. The red region is identifying the portions or the number of times that you're going to reject the null hypothesis when it is actually true. This is because of your standard of judgment, which we have set in this example to be 2.5%. And we set this ourselves. This is the value of alpha, and we can actually change this to any value that we desire. But if we change this, this is going to affect the other kinds of errors as well. So in this case, you have probability of doing a type 1 error is 2.5%, and the probability of doing a type 2 error is 9%. But if you change the probability of doing a type 1 error to practically 0 by taking the critical value very far away, you're actually ensuring that you will never be falsely rejecting the null hypothesis. But another byproduct of this is that even when the alternative hypothesis is true, you will not be able to detect it. As shown in the figure here, you have a larger yellow region, which is indicating a higher type 2 error. So as is obvious from this slide, there is a trade-off, and we have to write this trade-off. Depending on the kind of test we're doing, we have to set the value of alpha appropriately. So the value of the type 2 error is actually known as beta, and we can set it to a value of 0 if we can tolerate higher number of false positives. अगर हम अल्फा की वैल्यू ज़्यादा बढ़ा देंगे तो बीटा की वैल्यू कम हो जाएगी. But again, as was mentioned earlier, there is a trade-off. If you are gaining on one aspect, you are losing on the other aspect. Also, we have something known as the power of a test. एक statistical hypothesis test की power हम रेफर करते हैं उसकी ability को कि वो detect कर सके the alternative hypothesis is true when it is actually true. So this is actually dependent on beta, because this is calculated as 1 minus beta. If beta is very small, your power is very high. So in this case, to improve the power of the test, we can actually increase the value of alpha. So if we increase the value of alpha the power of the test actually improves a lot. Earlier, you had the power of test as 91%, but because the value of beta has decreased, the power of the test has improved. So again, there is a trade-off between alpha, beta, and the power of the test. So another important aspect is the power of the test is specific to the alternative hypothesis. Again, let me reiterate, what is the power of the test? Power of the test का मतलब है कि जब alternative hypothesis true है, what is our chance of actually detecting it? So this actually, the probability of successfully detecting the truth of the alternative hypothesis actually depends on the value stated by the alternative hypothesis. If it is very far away, as is shown in the slide, because the distance here is very far away, the power of the test is 100% because it is in the rejection region. So anytime you are in the rejection region, you would be automatically rejecting the null hypothesis. So इस case में आपका power of test 100% है. But it would be very low if the alternative hypothesis is specifying a value which is very close to that hypothesized by the null hypothesis. So in this case, you see that there is a large value of type 2 error, approximately 61%, and the power of the test is only 38.9%. This is because both of the hypotheses are predicting results which are very close by, and we cannot really distinguish between the result being produced by the null hypothesis and that produced by the alternative hypothesis. We cannot reject the null hypothesis in this case, even when the alternative hypothesis may be the real cause. So in this case, the power of the test is low. And lastly, the sample size is very important. And it is very important, especially if the difference between the means that you're trying to evaluate, the difference as proposed by the null hypothesis and the difference as proposed by the alternative hypothesis are very close by. By taking a larger sample, the standard error of the sampling distribution would reduce. And because of that, you can actually distinguish between the area that is produced by the null hypothesis and the area which is covered by the alternative hypothesis. And because of that, as shown here, if you have a sample size of 5, you would have the power of test as 100%. So with this simulation, I hope your intuition is built about how the different error works. So I'd be now wrapping up this discussion by making just two brief remarks. The first remark is that the scientific method requires us to rigorously analyze any hypothesis or any claim before it is adopted. And statistical hypothesis testing provides us a framework in which we do not adopt a hypothesis before thoroughly checking it. Secondly, a very important point, that in hypothesis testing, we are not trying to establish or trying to prove something. We are only trying to reject the null hypothesis, or we would fail to reject the null hypothesis, and this thing is in the light of evidence. If the evidence is so very great, then maybe you can say that we have proved something. But in most practical cases, it's not a question of proving something, it's a question of practically taking decisions in the light of evidence, taking the most appropriate decision. So with this, I wrap up the discussion. I'll see you next time, inshallah. Assalamu alaikum.